The last segment that I want to work with you today is other applications of work. Okay, there's other applications of work. And mainly what I want to say here is other applications here. Other applications. Mainly what you can have, we're talking about the summation of the work in a system. Summation of the work. The summation of the work could be work boundary. It could be plus work paddle wheel. It could be plus work electrical. It could be lots of things inside of there. And so we have to think about all the other forms of work. We've spent a lot of time talking about this boundary work. But usually with a paddle wheel, which is basically a mixer, they're going to tell us how much work goes into the system. And it's from the surroundings into the system. That means it's going to be negative. Okay, so I say plus, we'll play plus a negative here. Electrical work, let's talk about electrical work because that's the one thing that's different. Let's look at the electrical work. So if we are dealing in electrical, we don't really talk about work as much as we talk about power. So that's where we go back to this power, electrical power. Okay. Electric motor. Okay. We have coming into this plus and minus, plugging it into the wall. And we're going to have some current I flowing through these wires. Okay. Now we're going to have a voltage between these two lines, and I've dealt with voltage as being, I've dealt with V already as being velocity and volume. So instead of here, I'm going to use voltage as being E for electromotive force or whatever that is dealing with here. That's what I'm going to deal with. Okay. So electrical motor, and let's make our electrical motor our system. Okay. Coming out the other end is going to be a shaft of some sort, and the shaft is going to rotate, and it's going to have some omega, which is going to be our angular velocity. And it's going to have T, tau, some torque. We're going to input in some power, electrical power. We're going to get out some shaft power. Okay. So let's talk about first the shaft power. Torque is going to be equal to the tangential force times the radius. So this is going to be equal to the tangential force times the radius. Okay. And the velocity is going to be equal to the radius times the angular velocity. Okay. I'm bringing this all up because remember what we said at the beginning of this lecture, that W dot is equal to force times velocity. Power is equal to force times velocity. Well, what is that going to give me? Force here is going to be tau over radius times velocity, which is radius times angular velocity. And we're going to end up with that W dot is going to be equal to tau times omega. So you're going to have to know out what the torque is that shaft produces, and you have to know what the angular velocity is, and that's going to be W dot shaft. That's going to be the shaft power. Now the electrical power, W dot electrical. You probably know this from your circuits class. It's just equal to voltage times current, right? So in our case, it's going to be voltage times current. Okay, now here's the thing. Shaft power is from the systems to the surroundings, so this is going to be positive. Electric power is going to be from the surroundings to the system, so thermodynamically we're going to have to put a negative sign on there. We have to put that negative sign on there because it is not given to us in the calculation. So when we do this, we're going to have our power, our net power going into our motor is going to be W dot electric plus W dot shaft. Okay, where this W dot electric is minus voltage times current, W dot shaft is positive shear force times, is torque times angular velocity. And we want this to be greater than 0. It doesn't make any sense to put power in and get less out. We don't want that. We want our net power to be positive. We want that motor to take that electrical power and turn it into more shaft power. Okay? Power is in kilowatts. It's usually in kilowatts. Sometimes it's in watts, but usually we're dealing with kilowatts. But you may see from time to time us in this class talk about energy, and that energy is in kilowatts, kilowatt hours. So I just want to talk to you to end today about kilowatt hours. Energy demand is energy used in a period of time. So if we have a 10-watt light bulb, and it works for 10 hours, it's on for 10 hours. It consumes 10 times 10, 100 watt hours of electricity. Okay, that's what you pay for, those watt hours. Or 0.1 kilowatt hours of electricity. Now, what is the demand? The demand that we need is just what the light bulb was, 0.01 kilowatts. So our demand was 0.1 kilowatts. That's what power we needed to run that light bulb. How much did we use? How much did we consume? For those 10 watts for 10 hours, we did 0.1 kilowatt hours, and that's what we pay for. Okay, so those are the two things I want you to understand from this as we end today's lecture. And that kind of puts a bow on this week. It puts a bow on our topic of work, and we will start on Monday talking about some new information about how to increase our understanding of the first law of thermodynamics. I'll see you then.